3i Atlas has already disappeared from most people's attention. The thumbnails are gone. The urgent threads have scrolled off the timeline. The hot takes have been replaced by the next crisis, the next discovery, the next outrage. If you dig far enough back, you can still find the old posts, the third interstellar visitor, the strange comet, the object that shouldn't behave like this, but in the daily noise, it feels finished. The visitor arrived, it did something odd, it left. End of story. Except that isn't what happened, because while the hashtags faded, the measurements didn't. The object itself is receding into darkness, yes, but the data it left behind is not fading, it is sharpening, and in some ways it is becoming more unsettling, not less. 3i Atlas is past the headlines, but it is absolutely not past the data. That's the part of the story most people never hear. There is something deeply human about wanting cosmic mysteries to resolve cleanly. A strange object appears. Scientists observe it. It misbehaves. Debates erupt. A confident paper is published. A consensus settles in. And quietly, the textbooks absorb a simplified version of the explanation. We like our mysteries short, contained, cinematic. 3i Atlas refused to cooperate. Even while it was still dominating headlines, cracks were already forming in the final story. The first crack was the size problem. When 3i Atlas was first detected far from the Sun, near Jupiter's orbit, it was unusually bright for its distance. Early estimates suggested something enormous, possibly tens of kilometers across. An interstellar body large enough to make people quietly double-check orbital calculations, even if there was no danger. But as higher resolution observations came in, that picture collapsed. Hubble and other instruments narrowed the estimate down. Kilometers became fractions of kilometers. Eventually, some models converged on something less than a kilometer wide. Hundreds of meters. A small object. And that's where the real problem began. Because the activity didn't scale down with the size. Despite its shrinking physical estimates, 3i Atlas produced a massive coma, long, coherent tails, sustained gas outflow, dust structures spanning millions of kilometers. If you model it like a normal comet, porous ice, dust, sublimation-driven jets, the math starts to strain. A body that small, outputting that much material, should be destroying itself. Small, hyperactive comets in our own solar system don't stay intact. They fragment. They shed pieces. They turn into debris fields. 3i Atlas did not. Even in late-time observations after perihelion, the central condensation remained singular. No chain of fragments, no obvious breakup, no smoking gun of catastrophic failure. Small body, huge output, still coherent. That contradiction didn't go away when attention moved on. It became harder to ignore as the models improved. While some researchers were wrestling with mass and acceleration, others were focused on the dust. Most cosmic dust is tiny, sub-micron grains, so small that sunlight can push it around easily. That's why ordinary comet tails point away from the sun. 3i Atlas produced something different. Alongside a normal tail, it developed a structure pointing roughly toward the sun, an anti-tail. At first, this was dismissed as perspective, an optical illusion caused by Earth crossing the comet's orbital plane. That explanation failed. Detailed geometric modeling showed the structure was physically real, not a trick of alignment. To exist in the way it did, sharp, coherent, persistent, the dust had to be unusually large. Not smoke-like grains, but particles around 10 microns across, large enough to resist solar radiation pressure, small enough to still be lifted and organized by gas flow. That already puts the dust in a very narrow physical regime. Then came another strangely specific result. When researchers estimated how densely packed those grains had to be to produce the observed brightness, they landed near an optical depth of 1. Not thin and transparent, not opaque and black. Right at the threshold where the cloud marks obscures what's inside. While still scattering light efficiently from an engineering perspective, that's an almost ideal configuration for a dust veil. From a natural perspective, it demands explanation. You can tell a natural story. Feedback loops between dust shading, surface heating, and venting could self-regulate the system. That story isn't impossible, but neither is the alternative. The important point is this: the dust doesn't disappear when the object does. Those grains are now part of the solar system. They will spread, stretch, and drift along 3I Atlas's trajectory for years, possibly decades. Future spacecraft may encounter them. Future studies of zodiacal light may trace anomalies back to them. Meteor streams may one day carry material that was not born around our sun at all. That's what "not past the data" actually means. Another part of the puzzle lives in the object's trajectory. Public summaries often imply certainty. Here's the orbit. Here's the closest approach. Here's the outbound path. But if you follow the actual ephemeris updates, a different story emerges. As 3I Atlas became active, its outgassing introduced measurable non-gravitational acceleration, tiny thrusts from gas and dust jets. That's normal for comets. What wasn't normal was how difficult it was to model. The best fit thrust vectors shifted. The magnitude refused to stabilize. Even after perihelion, when activity should decline, the object continued to require non-gravitational terms to match observations. Early reports were confident. Later ones became cautious. Phrases like increasing uncertainty, trajectory sensitive to continued activity, extended non-gravitational effects began to appear quietly in technical updates. The object was never a danger, but it also never behaved like something simply falling through the solar system. Even now, outbound observations are still being used to refine the fit. If the extra thrust finally fades, that supports a natural, if extreme, comet scenario. If it doesn't, then 3I Atlas wasn't just unusual on approach. It was unusual the entire time. Either interpretation forces new models. This story isn't just about one object, it's about timing. We have now seen 3 confirmed interstellar visitors. The first shattered assumptions about shape and acceleration. The second expanded our understanding of comet chemistry. The third combined extreme activity, structured dust, and persistent trajectory anomalies into a single case. Each one forced an upgrade in how we think about what passes between stars. And this matters because we will see more. Surveys are improving. Detection pipelines are faster. The odds that 3I Atlas was the last interstellar object we ever observe are effectively 0. Which means this quiet period, after the hype before the next alert, is when the real groundwork is laid. The late-time photometry, the dust evolution models, the extended orbit fits, the radio silence constraints, these will become reference points. When the 4th object arrives, people will ask, does it behave more like Borisov or more like 3I Atlas? When the 5th one surprises us, its dust will be compared to this dust. When the 6th refuses to follow gravity cleanly, this will be the precedent. That's why the people who live inside the data haven't moved on, even if the rest of the world has. 3I Atlas is no longer breaking news, but it has quietly become something else, a benchmark, a stress test, a reminder that interstellar space may be delivering objects we are not yet prepared to classify cleanly. Whether it was an extreme natural comet, a fragment shaped by processes we don't yet understand, or something in between, the honest answer is the same. The case is still open. The dust is still spreading. The orbit is still being refined. The comparisons are still being written. The universe hasn't moved on, and neither has the data.